Hey everyone, and welcome back for another deep dive. Today we're going to try to tackle a pretty complex topic.
Oh yeah.
String theory. We're basing this deep dive on an essay by Jörg-Owe.
Okay.
And so to kind of set the stage here, string theory basically says that the universe isn't made of these like little tiny point particles.
Right.
But instead they're these tiny little vibrating strings.
Huh.
So like just seriously tiny.
Yeah, that's a pretty wild idea. I've heard of this before, but yeah.
Yeah, so it gets even crazier because, like, you know how we have all these different particles in the universe, like electrons, quarks,
Yeah.
all that stuff. Even the graviton, which is like the theoretical particle that transmits gravity.
Right.
String theory says that those are all just different vibrations of these tiny little strings.
So it's like all the different particles we see are just like different notes
Yeah.
on a cosmic guitar string or something.
Right, like a cosmic orchestra.
Yeah.
Where each string is playing a different note, and that's what makes up like all the matter and energy that we see in the universe.
That's a really cool way to think about it.
Yeah. But before we get too carried away,
Yeah.
I think we need to like take a step back for a second.
Okay.
What is string theory really trying to solve? Like, what's the big problem in physics that it's trying to address?
Well, one of the biggest mysteries in physics, and one that's kind of plagued physicists for decades, is how to make gravity and quantum mechanics play nice together.
Yeah, like they just don't get along.
They just don't get along at all. Quantum mechanics, describes the world of the very small, like atoms and subatomic particles, and it works incredibly well at that scale.
Right.
But then you have general relativity, which describes gravity and, planets and stars and galaxies, and that also works amazingly well on those large scales.
Yeah.
But when you try to combine the two, like when you try to describe what happens at the center of a black hole, where you have incredibly strong gravity and incredibly small scales, everything just breaks down.
It just doesn't work.
It just doesn't work. The math goes haywire. You get infinities popping up everywhere.
Yeah, it's a mess.
It's a mess. And that's where string theory comes in. It's like this grand theory of everything that tries to bridge the gap between these two seemingly incompatible worlds.
It's like the ultimate peacemaker in the universe of physics.
Exactly.
So in a way, string theory is trying to be like this unifying theory that explains the entire universe.
Yeah, that's the hope. It's a really ambitious goal. But there's this other thing about string theory that always kind of trips me up.
What's that?
The whole extra dimensions thing.
Oh, yeah, that's a big one.
I mean, I can wrap my head around the usual 3 dimensions, length, width, and height.
Right, right.
But string theory says we need more, like a lot more.
Yeah, I think I remember reading that it needs like 6 or 7 extra spatial dimensions.
Yeah, something like that. It's mind-boggling to even think about.
It really is. Like, where are all these extra dimensions hiding?
Well, that's the thing. They're not like these big, vast spaces that we just haven't discovered yet. String theory says that these extra dimensions are curled up incredibly tightly, like microscopic little origami shapes.
Okay, so they're not like entire directions that we're missing.
No,
Not exactly.
It's more like they're hidden within the space that we already know.
Exactly. Imagine like a garden hose.
Okay.
From far away, it looks like a one-dimensional line, right?
Mm-hmm.
But if you zoom in, you see that it has this circular dimension that's wrapped around itself.
Oh, I see.
So in a similar way, these extra dimensions in string theory are just so tiny that we can't perceive them directly.
That's a pretty neat analogy. I think I'm starting to get it now.
Good. Because it gets even more complicated.
Oh, no.
Because remember how we were talking about strings being like these tiny little vibrating things?
Yeah.
Well, string theory also says that there are these other objects called branes.
Brains. Like membranes.
You got it. They're like higher dimensional objects, so like surfaces or even volumes, and they can have strings attached to them. Wait, hold on. So you're telling me that not only do we have these tiny vibrating strings,
Yes.
but we also have these like higher dimensional membranes that they can attach to.
Exactly. And these brains are really important for understanding some of the most mysterious objects in the universe, like black holes.
Okay, black holes are already mind-boggling enough on their own.
Right.
How do brains help us understand them better?
So there's this really amazing idea called the add-SC-FT correspondence.
Okay, I've heard of that, but I don't really understand it.
It's pretty complex, but in a nutshell, it suggests that a universe with gravity like ours can actually be described by a simpler, lower dimensional universe that doesn't have gravity.
Well, wait, what? So you're saying that our universe, which has gravity,
Yes.
is like a hologram of a simpler universe that doesn't have gravity.
It's kind of like that, yeah. And the really cool thing is that these brains that we were talking about play a central role in this connection.
So by studying these brains, we could unlock secrets about the nature of black holes.
Exactly. It's like using this powerful tool to decode the mysteries of the universe.
This is getting pretty deep. Now, the essay also mentions this other crazy idea called supersymmetry, or SUSY.
Hi. Yeah.
From what I understand, it's basically saying that there's this hidden symmetry in the universe that connects different types of particles together.
Yeah, that's a good way to put it. Remember how we said that different string vibrations create different particles?
Yeah.
Well, supersymmetry proposes that there's this deeper connection between two main types of particles, bosons and fermions.
Okay, I vaguely remember what those are. Remind me again.
Sure. So bosons are like the force carriers. They're the particles that transmit forces like the photon, which carries the electromagnetic force.
Okay.
And then you have fermions, which are the matter particles. These are the things that make up stuff like electrons and quarks.
Right.
So supersymmetry says that for every boson, there's a corresponding fermion and vice versa.
So it's like there's this underlying symmetry between the forces that govern the universe and the particles that make up everything we see and touch.
Exactly.
That's wild. So in a way, string theory, with all of its crazy ideas like extra dimensions, brains, and supersymmetry, is kind of trying to create this theory of everything.
It is. A theory that can explain all the forces and particles in the universe.
That's incredibly ambitious.
It is. But the big question is it all just beautiful math? Or is there any way to actually test these ideas?
Right, because the essay did mention some difficulties with experimentally proving the theory.
Yeah, and that's one of the biggest challenges facing string theory. The problem is that it operates at these incredibly high energy levels that are far beyond what we can achieve with our current technology.
So like we have this amazing theory that could potentially explain everything, but we don't have the tools to actually test it.
Kind of, yeah. It's like trying to study the structure of an atom with a magnifying glass. The tool just isn't powerful enough.
So are we just stuck then? Like if we can't reach these crazy high energy levels, does that mean string theory is untestable?
Well, not necessarily untestable. The essay mentions that there might be some ways to test it indirectly.
Okay, so like what kind of indirect tests are we talking about here?
Well, remember those extra dimensions we talked about?
Yeah, those tiny little curled up origami things.
Exactly. So the idea is that even though these extra dimensions are super tiny, they could have still left like subtle fingerprints on the universe.
Oh, interesting. Like what kind of fingerprints?
Well, one place we might be able to see these fingerprints is in the cosmic microwave background radiation. You know, that afterglow of the Big Bang.
Right. So it's like looking for clues from the universe's baby pictures.
Exactly. Think of these extra dimensions like tiny little wrinkles in the fabric of space-time.
Okay.
And these wrinkles could have influenced how gravity behaved in the early universe.
So by studying these patterns in the cosmic microwave background radiation,
right,
we could potentially figure out if these extra dimensions actually exist.
Exactly. It's like the universe is whispering secrets about its hidden dimensions.
That's pretty amazing. But the essay also mentions some criticisms of string theory, right?
Oh, yeah.
Like, even if it's a beautiful idea and mathematically elegant, some scientists aren't entirely convinced.
Right. And one of the biggest criticisms comes from what's called the landscape problem.
The landscape problem. What's that?
Well, remember how we were talking about those extra dimensions needing to be curled up in these specific ways?
Yeah.
It turns out that there are like a ridiculous number of ways to do that.
Really?
Yeah, like countless ways. And each different way of curling up those dimensions leads to a different possible universe with different laws of physics.
So it's like a multiverse of potential universes.
Yeah, kind of like that. And that's a problem. If there are so many possible solutions, it becomes really hard to make specific testable predictions.
I see. So it's like having too many answers is a bad thing.
Exactly. It's like saying I have a theory that can explain anything, but I can't tell you exactly what it predicts for this particular experiment.
Yeah, that wouldn't be very useful.
Right. So some scientists argue that this makes string theory almost unfalsifiable.
Unfalsifiable. What does that mean?
It means that you can't really prove it wrong.
Oh.
Because no matter what the experimental results are, you can always just tweak the theory to fit the data.
I see. So for the theory to be considered truly scientific, it needs to be falsifiable.
Exactly. It needs to make clear predictions that can be tested.
And if those predictions turn out to be wrong, then the theory needs to be revised or even abandoned.
Right. And another criticism of string theory is that it relies on this idea of supersymmetry.
UA?
Yeah, is UEY. And so far, we haven't found any experimental evidence to support it.
So that's a pretty big missing piece of the puzzle.
It is. And because of that, some physicists are starting to question whether string theory is really on the right track.
So it's a pretty heated debate then.
It is, yeah. There are some strong opinions on both sides.
So where do things stand with string theory today? Is it still an active area of research, or are people moving on to other ideas?
Oh no, string theory is still very much alive and kicking.
Mm-hmm.
There are tons of brilliant physicists all over the world who are still working on it and coming up with new ideas.
That's good to hear. So what's the future looking like for string theory research?
Well, one thing that's really exciting is the possibility of exploring what happened before the Big Bang.
Way before the Big Bang.
Yeah. Traditionally, we think of the Big Bang as the beginning of everything.
Right.
But string theory opens up this possibility that there might have been something before that.
Really?
Yeah. Like maybe the universe goes through cycles of expansion and contraction, or maybe there was some other kind of pre-Big Bang era that we don't even understand yet.
That's mind-blowing. So it's not just about explaining the universe we see now, but also what might have come before.
Exactly. And there might even be clues about this pre-Bangian era hidden in the cosmic microwave background radiation.
So we might be able to use that to test some of these ideas about what happened before the Big Bang.
Exactly. And beyond pre-Bangian cosmology, there are also a lot of efforts to combine string theory with other promising theories, like loop quantum gravity.
So it's like trying to find a bigger picture that encompasses all of these different ideas.
Yeah. Maybe a synthesis of different theories will ultimately lead us to a more complete and unified understanding of the universe.
I like that. So even with the criticisms and the challenges, there's still so much to explore and discover.
Absolutely. It's a really exciting time to be a physicist.
And speaking of exploring and discovering what's next for us in our deep dive into string theory, yeah, it really does feel like we're just scratching the surface of something huge with string theory.
Oh, definitely. And it's been a long journey to get to this point.
Yeah, how long has string theory been around anyway?
Well, the origins go all the way back to the late 1960s.
Really? That long?
Yeah. It all started with a physicist named Gabriele Veneziano. He was trying to understand the strong nuclear force, the force that holds the nucleus of an atom together.
Right.
And he stumbled upon this mathematical formula that seemed to describe these tiny little vibrating strings.
So the whole idea of string theory kind of came out of nowhere.
Kind of, yeah. It was this serendipitous discovery that sparked a whole new way of thinking about the universe.
That's wild.
Yeah.
So who were some of the other big names who helped develop string theory?
Well, after Veneziano, you had physicists like Leonard Susskind and John Schwartz who really started building the first string models.
Okay.
And then there's Edward Witten, who's considered like one of the leading figures in string theory today.
What did he do?
Oh, he did a ton of groundbreaking work. He came up with this idea called M theory, which is like a more unified version of string theory.
M theory. What's the M stand for?
Nobody really knows for sure. Some people say it stands for mystery or magic or even mother.
Uh-huh. So it's like the mother of all string theory.
Yeah, it's something like that.
So it sounds like string theory has been this really collaborative effort with all these brilliant minds building on each other's work.
Absolutely. It's a testament to the power of human curiosity and ingenuity.
Yeah, and what's really cool is that Schneeppert points out this interesting connection between string theory and pure mathematics.
Oh, yeah.
Yeah, he talks about these things called G2 manifolds, where these really complex mathematical structures.
Right.
And apparently they're important in both string theory and in pure mathematics.
That is pretty cool. It just goes to show how interconnected different areas of knowledge can be.
Yeah, it's like there's this hidden web of connections linking things that seem completely unrelated at first glance.
It really makes you wonder what other secrets are out there just waiting to be discovered.
Absolutely. Well, we've covered a lot of ground today in our deep dive into string theory.
We have.
So as we wrap things up, what's the one big takeaway that Schneeppert leaves us with?
Well, he ends his essay with a really thought-provoking question.
Okay, I'm intrigued. What is it?
He asks if string theory is actually the theory of everything, the ultimate explanation of the universe. Does that mean everything that can happen does happen?
Oh, that's a pretty deep question.
It is. And it really makes you think about the nature of reality itself.
Yeah, like if every possible vibration of those tiny little strings represents a different outcome, does that mean there are countless parallel universes out there where all the possibilities are playing out?
It's a mind-boggling concept, for sure.
It really is. Well, this has been an incredible journey exploring the strange and wonderful world of string theory.
I agree. It's been fascinating.
A huge thanks to Jörg-Owe Schneeppert for inspiring this deep dive with his insightful essay.
Yes, definitely.
And for our listeners, if you're eager to explore further, be sure to check out the show notes for links to Schneeppert's full essay and other resources.
There's a lot more to learn.
Until next time, keep those minds curious and keep exploring the universe.